How are you?
Hey, Haley, good. Let me make sure you can share. Great. Okay. Super, super,
Yep.
super. How are things on your coast?
Good. We had about 2 days of fake spring, which was lovely. And now we're back to 40s. So back to cold, but
Yeah. Yeah,
a glorious few days of 60 and sunny.
nice.
What about you?
We're having mildly insane weather for Seattle. Let's see if I can show you
Really?
it. So crazy. Is it showing? Ah,
I think you got a blurred background on. So it's
darn.
not.
Yeah, I have blurred, but anyhow, it's snowing heavily,
Wow.
which is nuts
Yeah.
for Seattle for March. It's
Right.
not normal. It's like
Is there
these,
like snow on the ground?
yeah, yeah. I mean, it's still warm, so it's melting really fast, but the roads
Yeah.
all have snow. And it's like these big old flakes like that. So
At least that's pretty. Big
wild.
snowflakes are pretty.
Yeah. So yeah, it's nice. Okay, you can share your screen.
Yep.
I will. That. Da, 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 da. Hi everyone, welcome to the Friday hack hours. I'm going to wait just a moment, let folks roll in. No, wrong place. Okay. All right, I am waiting just a moment as folks roll in. Let's see. Yes, that should be. Nope, nope. Recording, excellent. Add the link. It's not that. Okay. All right. All right, welcome everyone to the Friday Hack Hours. We are going to continue with our third installment on working with boosted regression trees in Python. And in the first session, you had kind of like a little introduction. You can look at that, it's linked there. Um, in the second session, Ryan Vandermeulen showed an application with some fish survey data, focusing a lot on like how do we create the data that we get into a boosted regression tree. And now today, I'm really happy that Haley Synan was able to join us. I've had the pleasure of being able to work with Haley at two different um, PACE Hack Weeks. And that's been really fun, working on projects that she's led using fisheries survey data and PACE hyperspectral data to improve like fish abundance estimates. And so today she's going to be going through a notebook that she and a team developed during our Fish Pace Hack Week that happened end of January. And I've asked Haley to focus a bit more on the like tuning aspects, the diagnostics aspects. She's not going to focus like so much on the data munging. We did a whole lot of that last week. Um, and also, I think Haley, you're going to use XGBoost also, which is kind of
Yeah.
a new. Yeah, so that's a package we haven't talked about. So you get to see how to use that. Um, Yes, James, the recording from last week is available. I messed up the first week, so I'm going to have to record that one separately. Fortunately, I was the one who gave that, so that's easy. Um, while Haley's talking, maybe I'll be able to add that video for that second one from Ryan. All right, so when you go onto the web page, and I put that in the link there. I'll add that again in case we had anyone joining late. So let's go here. So if you click on that, what you're going to see is some buttons. And you can, if you want to follow along, I mean, you're welcome to just listen, but if you want to follow along, you can run all this in Colab, or we also have a Jupyter Lab hub with everything set up. And this one that says NOAA is one that it doesn't have a persistent user home directory. So once you log off, your changes go away, but anyone from NOAA can log in. Um, we have this NIMS Jupyter Hub. So if the stuff that we are teaching in these hack hours are things that you would like to be learning and working on from week to week, maybe trying out some of your own things, you're welcome to reach out to me and you can be added to that Jupyter Hub. And then, of course, Colab is great. And I'll just show you if you haven't used that, you can click on this. It's automatically going to open this up. And Colab will have basically all the packages that Haley is showing, except for two. And so when you get down to this line here, and it says install SHAP or however that's called, you'll need to add one more package, and that's Cartopi. And that's it. Everything else is going to be available. All right, with that, I'm going to hand it over to Haley, who is going to show you this project. Oh, by the way, I should have mentioned that Haley is a ocean color remote sensing specialist with the Northeast Fishery Science Center. And beyond this project, she's going to be talking about, they're doing a lot of really interesting things with kind of water classification using PACE ocean color data.
Yeah, thanks, Eli. Let me share my screen here. Okay, did that go up? Apologies if it's small, but yeah, thanks, Eli. This was a project that came out of, like Eli mentioned, the Fish Pace Hack Week. So it was a group of about 7 of us, I think. We're all listed here. From all different places. We worked within a couple different time zones, which was really cool. And challenging at some points, right? Like some people were working at like midnight, 2 a.m. their time. So what we're going to do here is we are going to create a fish abundance model using optical data, so paste data. So a species abundance model, they're pretty useful in the context of fisheries. They can be used in stock assessments to assess stock health, be used to set quotas. And what I would be most interested in looking at shifts in species assemblages throughout time, like interannually and annually. So why include optical data? Typically, right, when you think about what's going to go into a model, there's a lot of environmental drivers, so like temperature and salinity, which are really important. But the optical data helps you get at like the biology, right? So it's proxy for phytoplankton biomass and the chlorophyll and kind of gets at what's in the water. So the data sets we're using here, we're using 3 cruises from the NOAA NEFSC bottom trawl survey. And this was because that was what was available to match up with the PACE time series, right? PACE was launched in spring of 2024, and bottom trawl survey, they go out twice a year. So at the time of this hack hour, there were 3 cruises available for us to work with. Then we are grabbing some PACE RRS values. And then this was some interesting, someone in our group, Leandro, introduced us to this data set. It is FSLE, which is finite size Lyapunov exponents. And so they're like a Lagrangian diagnostic that kind of gets at boundaries of water masses. And it kind of highlights fronts and any kind of boundaries like that. And then we also have wind stress curl that we included. So this is what we're going to go through. And if you're looking at it locally, you can click this and it will take you there. So first, we're going to import all of our libraries. And so the way this is set up, because we were working in a group, we had a couple people matching data and then a couple people working on the modeling. So we're going to just merge some data that was already matched. So we're not going to go over that part. But we're just matching the bottom trawl data to the remote sensing reflectance matchups and the FSLE and wind curl data. And so once we have that matched, this is what we end with here. Let me just make sure I'm actually running this. Okay, so then we're just going to do a little bit of data cleaning, just adding some month, day of year, stuff like that. And the biggest thing we're doing here is we're going to log the catch data, right? So there's a column there's a lot of columns in here, but there's one column that is the number, like the count that was caught of hake that was caught at that station. And so we're just going to use the logged values of that. So at this point, yes, Eli.
Is it possible to increase the font size a little?
Try to zoom.
Great, thank you.
Sorry, that might cut off some things here, but some of the text, but yeah, sorry, I know it's small. I tried to make it bigger, but Markdown was not happy with me. So, okay, so at this point, we want to split our data into testing and training data. Now, with oceanographic data, you want to do a temporal split. So you would want to, like, in this example, if we have 2 cruises from 2024 and 1 from 2025, you would really want to use like the 2024 as the training data and the 2025 as test data. And that's because when you split it randomly, you get data leakage, which if you're following along, I made some definitions of things that people might not be clear on. So if you can just hover your cursor over anything with a hyperlink and it'll tell you. But essentially, when you split up randomly testing and training, right, the cruise is over a couple weeks. So there's a good chance that there's going to be data from the same day or a day apart in the same location in the testing and the training data. And that's going to make the model like learn explicitly when this is it, this is the response, right? And that's not something we want. So that's why you typically would want to split it temporally. With all that being said, here we are splitting it randomly. And this is just because we have a very small data set, right? Like there's 192 rows, observations, and that's not a lot. And also, when we were writing this came together very quickly, right? Like the hack week was a week long. But we wrote this part very quickly, and there's just not a ton of data. And so we did it randomly. I would not recommend doing that. It's not something you would want to have enough that you can split it temporally, but just for the purposes here, we're splitting it randomly. So then we look at our data frame, and from this, we have our catch data, and then from the crews, while they're out there, they're getting CTD, dropping a CTD and getting salinity and temperature values. And when we look at it, we're missing a lot of that data from our already limited data set, right? And so that's not ideal. In a boosted regression tree, typically you can give it NANs, but it typically just won't look at those NANs. It'll disregard the whole row. And that's not something we really want because we already have such a small data set. So we are going to impute that data. This can also lead to additional errors in the model, right? Because now we're giving it guessed data, right? Not ideal, but for the purposes of this is what we're doing. So then we get into the actual boosted regression tree, which I think you guys have went over. So we'll get into the feature selection. So PACE data, right? There's 172 wavelengths, I believe, right? And that's going to be, and they're at a 2.5 nanometer step. So not every wavelength is going to be giving us new information. And so in a model like this, we don't want to include all of those. It would confuse our model and not be great. So we're going to do some band selection. So what we're going to do here is, well, this is first a correlation heat map. So we can see there's a lot of multicollinearity here, right? Like a lot of the wavelengths are very, very correlated, which is why we need to do that. We need to do some selection. So the first thing we're going to do is we're going to run a model on all of the wavelengths, so all 172. Then we're going to rank them by their importance in informing the model. So we're going to get the number one most important RRS, and then we're going to do a correlation matrix of that most important band and all the other wavelengths. And we're going to drop any wavelengths that are more than 95% correlated. So that will, 95% is still a lot, but for the purposes of this is what we're doing. And that will reduce some of that correlation. And then we're going to run that again over and over. So once we drop, we get our first band, we get values that are less than 95% correlated. And then we drop those. And then we're going to run it again, that initial boosted regression tree on now that subset of remote sensing reflectance. And we're going to iterate over that until all of the bands have been handled. So this will run. And so it's going to tell us on the first one, 452 was the most important. And so then it's going to look, and probably some of the other 400s got dropped, right? And then we've got 600. And so this is just ensuring that we are trying to reduce the correlation between any of the wavelengths that we're putting into the model. So then here, we're just going to add our other ones that we're going to include. We didn't do any feature selection on these just because we were interested in seeing the impacts of these variables on the model. So we've got bottom temperature, bottom salinity, depth. We've got this FSLE and the curl stress and the day of year. So these are the final variables that we're going to be putting into the model. So at this point, now we're going to hyperparameterize some of the parameters in the model. So the ones that we are going to hyper optimize are listed here. And so N estimators looks at the, yeah, Eli? You're muted.
There's a question in the chat. Someone says their wavelengths are different.
Yeah, that is probably just because, yeah, the data was split randomly, and so it's not guaranteed to be the same. Like I could run this a bunch of times with different data and it's gonna pop out looking differently. Um, so yeah, the first thing we're gonna hyperparameterize is the number of decision trees that are being built. And then the next one is max depth. And so this is looking at how complex each tree is. And so a lower max depth means the model is going to be more simple, and a higher max depth means the model is going to be more complex with more leaves. Then we're going to control the learning rate, which tells it how quickly to learn all the data, right? So slowing it is going to prevent overfitting. And typically a lower learning rate, you need a higher number of trees to balance that. And then these next two here, reg alpha and reg lambda, control the L1 and L2 regularization terms. And so these are just controlling the loss function of the model. And so what we're doing here is we're setting up this grid. And so we're saying for number of trees, test 100, 200, and 300. And same for learning rate in all of these. So you could put in whatever you thought might be a good idea. Here, we're only asking it to test pretty small max steps because we don't have a lot of data. So we don't want the model to be overly complex because we don't want it to overfit. So these could be interchanged just depending on what data you're using and such. This is just what we chose to do. And so what's going to happen is it's going to use this grid search function, which is going to run all of these with these different parameters. So it's going to run the model with all these different parameters, and it's going to spit you out what it thinks the best is that will give you the best value, like the best R-squared values and the best fit. So at this point, we say, thank you very much for that. And now we will put that into the final model. So here we're saying use everything that the grid search said was best to use. So now our model is run and we can look at our feature importance. And this is built into sorry, I should have said this before. This is using the XGBoost. And it's really quite nice to get at the feature importance. It gives them to you already, and you just need to plot them essentially or look at them. It's built in and it's pretty nice. So here we can see max depth is going to be the most informative. That makes sense. And so from the most informative here to the least informative up here. And then we are going to now predict our Silver Hake abundance on our test data. And so we've got an R-squared of 0.43, which is not bad, right? So off the cuff, doesn't look too bad right now. And now we are going to visualize our results. And I have them plotting in, okay, let's zoom out a little bit there. This is the raw count data. And then I also have them plotting on a log scale. I know some people's brain works better with log scale. I am not one of those people. I prefer to look at the raw, but both are there for your preference. And we can see here off the bat that we are having some underestimation issues at high counts, right? And so I should note here that in the plotting, we set the maximum here to be 1,000. And that was just to be able to look at how they were doing at lower values as well. But when we get to the one-to-one scatter plot here, we can see really, really underestimating, right? Quite a bit. And so that could just be there's not enough data. There's not enough representation of the data in the training data set versus the test. It's probably going to come down to our really small data size, right? So now we're going to map the residuals here, again, we have it on the raw scale and log scale here. So now we see this severe underestimation here in our predictions, and we want to see how each of our input features is impacting the model. So we are going to plot up some partial dependence plots. And so these are going to isolate the effect of each variable's impact on the model. So, oh, it's still thinking about running. Anyways, the variable name will be on the x-axis and the catch will be on the y-axis. This should not be taking so long. That's okay. We'll wait it out. But essentially what it's going to, oh, here we go. Okay, so what we see here is the, for example, max depth, right? So we have this nice, generally increasing, right, as we go with depth. So this is going to say at higher depths, there's more catch. So a lot of these, like it says up here, this is, I kind of put some details on how to interpret them. If we're looking at a noisy line, that's generally indicating that something's gone awry. Like the predictor's weak, there isn't enough data, or the model's overfitting. So we look here and we're seeing a lot of noisy lines, right? Like this is very noisy. This is very noisy. A lot of these have very, very jagged curves. And my guess here is we are having a lot of this, not a lot of data, right? It really didn't have that much data to train on. And we're having some overfitting. But this just lets, the partial dependence plots lets us look at how each individual feature is impacting the model. Then we are also going to look at some bland Altman plots. And so these are a way to visualize agreements between two of them. So on the red here, this red line is the mean bias. And then these gray lines here, these gray dashed lines, are the limits of agreement. And so the limits of agreement are the range of which 95% of the values should fit in. And it is calculated here, and it is the mean plus or minus 1.96 times the standard deviation of the data. And so what we can see from this plot here is the mean bias line, like we saw, we're underestimating, right? So the mean bias line is that showing that our predicted catch is underestimating real catch. We also see here very, very wide limits of agreement. And that's just going to be because we're underestimating so much. Those limits of agreement are getting pushed pretty wide. Okay. And then we also are going to plot some SHAP values. And these assign an importance value to each feature that you use to train the boosted regression tree. And this is kind of funky. I don't quite know how this works, but it uses game theory, which I thought was really interesting. But how to interpret this. So we have each of our features here, and we have our 0 line here. So anything above 0 meant that that was pulling the model to predict higher abundances, and anything here was pulling it to predict lower abundances. And then on this color bar, we have what the actual value of that feature was. So pink is high. So we're saying high depths pulled the model to predict higher abundances, which is similar to what we were seeing in this partial dependence plot, right? Catch is going to be higher at deeper values. And now we get to the fun part. We're going to be checking for overfitting. So how we're going to do that is we're going to take our training data and our training data and get an R-squared value from that, and then our test data and get an R-squared from that. And we're going to look at the differences. So our training R-squared was 0.81. And our test R-squared is 0.43. And so generally, we would want to see those R-squared values be a little bit closer together. So right off the bat, like a really high R squared in your training data might mean the model's overfitting. And so typically they say if there's a 10 to 20% difference between your two R squareds, that's a pretty good indication that your model's overfitting. So here we have about a 0.4 difference, which is going to indicate that the model's probably overfitting. And finally here, we're going to do some cross-validation. And so this would be evaluating the model's performance. So it's going to split the data set randomly. So this we're putting now going back away from our original testing and training data, and we're giving it the whole entire pool of data. And it's going to split it again 10 times. So it will randomly split the testing and training data and look at those R squareds, and it will do that 10 times. And so we have the average here, and we're seeing a pretty similar. So this is the average RMSE and the average R squared of those 10 separate splits. And so we can see that the R squared of 0.416 is pretty similar to what it was off of our first one, which was 0.42. So I'm sorry if you can hear my dogs. So generally it's saying like the model's pretty stable, like the data is saying the same things no matter how you split it, but we're still having an overfit problem regardless. So how would we want to improve this model? Obviously, the number one thing is going to be more catch data. Something I should have mentioned at first, I believe that we only used presence data. So we only included data where hake were caught, including absence data would have been really beneficial for a model like this. But I just don't think we had the time for that. But again, so more catch data would have been great. So you can either wait, right? Like I said, the bottom trawl survey goes out twice a year. So in a year or two, there will be more data to use. Or the bottom trawl survey has been going for decades and decades. So if you wanted to get at a longer time series and use some more historical data, using a satellite that's been around for longer would get at having a longer time series to be able to use in your training. The downside there is you're only going to have multispectral bands available. But having more data again would help with that overfitting. Also, something that would be really cool would be to test some other pace variables. So chlorophyll, apparent visible wavelength, which was developed by Ryan Vandermeulen, looking at photosynthetically active radiation. And Moana was something we really wanted to incorporate but didn't have time. So Moana is a pace product that looks at phytoplankton groups. So it has will tell you where Synechococcus and Prochlorococcus and Pico eukaryotes are, which is really cool. And so some limitations of this, the use of imputed data probably did not help our overfitting problem. That would have been ideal to either have more data, so the imputation mattered less, right? Like I think we imputed 60% of the temperature and salinity values, which is a whole lot. Obviously, the small data set's going to be the biggest thing here. So the model was likely memorizing specific values and not fitting to the actual patterns of the data. And again, like I mentioned, we're doing the random training split. That's not typically what you want to do. So that's a limitation in this model as well. But going to here, what's a good data size? What I've read is you want to have at least 10 observations per feature that you're incorporating. So we had probably 13 to 15 features that went in. So we had, 14 go in. And I believe we were training on like 130. So we would want at least 140, but obviously more is better. More is always going to be better. But as a rule of thumb, I've heard at least 10 observations for every feature. So, I mean, we could have tried using less features, cutting it down to less of this. But again, this was just something that we created for the Hack Week. So that is all I have. I'm happy to take any questions or comments or anything like that.
All right, super. Thank you so much, Haley. That was really great to see all those statistics and diagnostics that you were doing.
Thanks.
Yeah, because we hadn't gone into that at all.
Mhm.
So yeah, I guess one of the first things that I was thinking about was just about the features that you included.
Mhm.
And that was like, using some ratios. I know that that's what Ryan was doing when he was looking last week with with some other survey data.
Mhm.
Um, did you think about that, or do you think this captures some of that if you're having two wavelengths? I don't know.
Yeah, I think um I haven't gotten a chance to see exactly like what type of ratio that Ryan was including, right? But generally there's several wavelengths that are pretty informative of chlorophyll, right? And like that type of ratio. But yeah, I definitely think a combination of the two could be really cool. I wanted to do this correlation version just because that was something I'd never done. And obviously, with hyperspectral data, multicollinearity needs to be addressed. And so um, I just thought that this was an interesting way to get at that. But yeah, I do think like a combination of kind of incorporating what Ryan was doing. So almost starting with those ratios and then looking at the correlations from there would probably be even better.
All right. Any other questions for Haley or, about boosted regression trees in general? Also, if you've had experience with these and want to, throw in any comments, please do so. You can go ahead, just raise your hand or throw it into the chat.
Yeah, this was, I just want to add a comment. This was really cool because before the two hack weeks, so the first hack week that Eli and I got to work together at was the PACE hack week. And we did a similar thing with boosted regression trees, but we did a multi-species species abundance model. And that was the first time I'd done any kind of species distribution modeling. And so I really appreciate the hack weeks because it really gives you a time and space to just do something you've always been interested in, but never had the time or availability to do, right? And you just learn so much, and they were great.
So thinking back on this project, what was the hardest part of it? You talked about the time zones, but for like
Yeah,
the actual
yeah,
project.
yeah. The for the actual project, I would say handling, like, it's always the pre-processing of the data that gives you a little bit more trouble than you would like. So I would say the handling of the missing data, we at first like had tried dropping it, and I do think we did end up dropping anything that was missing in the paste data, if I'm remembering correctly. But at first we had tried dropping any of the missing data and we were left with like, I don't know, 50 observations and can't train on that. So I would say, yeah, figuring out how we were going to deal with our limited data set and make the best of it being so small. Oh, and something else I should mention, in boosted regression trees, you actually don't need to scale the data. You don't need to like normalize it, all the variables to be like typically like -1 to 1. You don't need to do that because it's not because the way that the boosted regression trees, which I'm not super familiar with, but to my understanding, they are looking at not necessarily the magnitude of the data, which is why you don't need to scale them. They're ranking the variables rather than looking at like the magnitude and difference between all the variables, which is, so I typically do a lot of like unsupervised learning. And so getting to switch to do some supervised algorithms was really fun.
Can you briefly explain the difference between the supervised versus the unsupervised?
Oh yeah, sorry. So the boosted regression tree here is a supervised algorithm. Right, we have our predictors, which we used our remote sensing reflectance and our environmental data to have our output, which was our catch data. Right, so we're saying when I give you X, tell me Y. Unsupervised learning, you don't have labels at all. So you're giving all the data to the model. You don't need to split it. And you're giving all the data to the model and you're asking it to look for like patterns and correlations, right? That like may not be observable to the human eye. So most clustering algorithms are unsupervised. But
oh, all right.
Yeah. Yeah.
All right. Again, feel free to raise your hand. Any questions or comments? I guess like one thing, a question I also had was you talked about having to do imputation. So can you remind me what were so weren't imputing for the missing pace data?
Yeah, because I think we had
Reflectance.
previously dropped the missing pace
Yeah,
data.
okay. So
Yeah.
what were the missing data that you were missing?
It was the temperature and salinity values that were taken like on the bottom trawl survey.
Yeah.
So they either didn't take it at that like typically they'll drop the CTD in and take it at like standardized depth. So they either didn't like take it at that depth or I could have been missing for a different reason. But yeah, so we did like a K nearest neighbor imputation. So looking at the value closest to it and giving it that same value. So it can add a lot of error and uncertainty when you're using imputed values on a model.
Right. Yeah, I wonder if you'd been able to use modeled data. There are some 3D.
Yeah, so
yeah.
We had thought about that. I think when we were talking about it, we were talking about using Glory's salinity or modeled or temperature because it's depth integrated. They've got a whole bunch of depths that they have the model data available for. But I think at that time we'd kind of tossed around the idea and then we didn't think as much of it was going to be missing as it was. And then by the time we realized how much of it was missing, we didn't have a ton of time left in the hack week. Right. And we're like, okay, well, we just gotta, get this part done. So yeah, I do think something else too is they probably either fill it in with modeled or just use the modeled or something else because if you look, let me share my screen again quickly. Temperature was not a super important in this specific model. Temperature wasn't a super important feature in this training, and that's something you would expect. So I'm assuming that's probably has to do with the imputation, right? Like it wasn't,
Right. Okay.
it's not getting the right signal because that data was imputed.
Okay.
It's
Yeah.
my hunch. I'm not sure,
Yeah.
but um,
Yeah. Can you also talk a little more about that that data layer that had like eddies and fronts? That's the first time I'm seeing that.
yeah, the FSLE.
Mm-hmm.
Yeah, so that was something I had also never heard of, and I'm not super familiar with it. But it's a product put out by Aviso. I can put in here it is. So it is data that is collected from altimetry. Um, and so I don't entirely know because I had also never heard of it, but it's a really cool concept. And yeah, John, have you heard of FSLE before?
Yeah, I haven't worked with them,
Yeah.
except sort of from the side. There's sort of boundaries in large oceanographic flows, and they use them for. I mean, they can be three-dimensional and things like that too. They use them for trying to understand turbulence around airports and a bunch of other places. So they've got a lot of different applications. There have been some applications in the Gulf of Mexico for trying to understand particle transport and things like that.
Mm-hmm.
Um, Oil spills, uh, fish larvae and egg transport and things like that.
Mm-hmm.
Really interesting things. It would probably be worth fooling around with. I am surprised that there's so little because these boundaries would be boundaries between water masses with fairly coherent properties. So
Yes.
you're dividing things up in a way, and but they don't show up here. And
Mm-hmm.
I wonder why that happens that way.
Me too. I that was also something that I kind of flagged as well because yeah, how it was explained to me exactly what you said, right? It's boundaries. I believe Leandro, who was in our group who brought up this FSLE, he calls them like the fences of the ocean, right? So they get the boundaries, right? So I was also kind of surprised that it wasn't such an important feature in the model. I don't know if that would change with like a slight tweaking of how it was included or something else, but because inherently, like what it is, I would also think that it would be important. But
I mean, there's some really cool stuff in terms of transport with some of these
mm-hmm,
boundaries. If you had like an AUV or an autonomous underwater vehicle, you could look at these patterns and you could find places where you get this vehicle from one place to another much faster than just a straight steam across. So you can take advantage
mm-hmm,
of the structure of the flows around these structures to transport things much more rapidly than you would think you could. So they are really
hmm.
interesting. Yeah.
Yeah, I know. Once he like explained what they were, it's definitely something I want to bring into my work because, like you said, yeah, there's some like really cool applications for it.
Yeah,
Yeah.
I mean it's for fisheries and things like that. It's not only the biological pieces of transport, it's also
Mm-hmm.
transport of material, right? So it could be nutrients, it could be productivity signals that are moving from one place to another, where it's generated one place and taken somewhere else where it's used. So there's a lot of linkages that you could explore with these things. Um, it would be fun. It would be fun to fool around with it and some paste out. That's really interesting.
Mm-hmm.
Yeah.
Um, Ben, do you want to unmute and talk a little bit about how you used it for whale shark movements?
Can you hear me?
Yep.
Okay. Yeah, well, we tried to use it. It was like a model we were trying to use to see what might be influencing whale shark movements in the Gulf of Mexico. And, I think someone already mentioned it. The temperatures are just so homogeneous there that, you don't get much distinction in terms of temperature a lot of the year, and even fronts are unrevealing in those cases. But FSLE uh, is always there and always has like some contrast. So and also from a relational standpoint, you're talking about transport. It can also be an aggregator. Whale sharks are filter feeders. So it could be indicative of somewhere they're feeding. We did not finish the work yet, but I had heard of the product when when you brought it up.
Yeah.
I would really be interested in seeing like what comes of that, because that sounds really, really cool.
Yeah. Ben, do you have any like preliminary sense of whether it's going to be informative, or is it too early?
I don't know where the project is at, honestly.
Oh,
It kind of got started, and then it was just a small part of it, and I don't know where it's at right now, honestly. But I remember using it. I will resurrect it. Say there's a lot of interest.
yeah, I've definitely been, over the last couple of years poking around, like wanting to find some kind of product that would be easy to use, that measures your fronts and also eddies. And it's really easy to find the algorithms. And I'm surely the products are out there. I just haven't found them yet. Doug, go ahead.
Yeah, this is great. Thanks a lot. These have been really helpful and very, very informative. I just had a sort of general question for somebody who's dipping my toes into the machine learning world and realizing that there probably are going to be some applications where I at least want to try it out. But I'm curious are there any kind of like general guidelines or rules of thumb, like a priori, where you can say, given your data or what you're trying to do, you should go with a boosted regression tree. That's the way to go. Or, you should go with random forest. Or is it, I've seen some papers, they try them all, compare them. Is that sort of the general approach, like just apply all the different models, all the different techniques out there and see what works best? Or do you know sometimes like, yeah, which one's going to be best for the type of data, the type of thing you're trying to do?
Mm-hmm. Yeah, in this context, I don't know any rules of thumbs, but actually our original, so I adapted this tutorial from our original Fish Pace Hack Week, which I will put in the chat here. But there we actually compared random forest and boosted regression trees. So I think at least between the two, boosted regression trees are generally a little bit better. I think because they're sequential learners, right? Like they learn from the error of the last tree, compared to when they learn in parallel. But generally, like, right, when you've narrowed down, this is the data I have, this is what I want from it. In the terms of supervised stuff, I don't know as much, but like in unsupervised learning, maybe it's applicable in supervised learning. You typically want some algorithms are better at handling noise. So if you have noisy data, you'd want something that's a little bit more robust for that. I'm sure there are some guidelines or rules of thumbs that I'm just not sure of, but generally like looking, at how it handles noise, how it handles outliers, how computationally intensive it is also kind of something that's important to look at. But generally, I don't think I have a great answer for, unfortunately. I'm sure there are answers out there, though.
Thanks. No, that was great.
Yep. I've two types of models that I often contrast are convolutional neural networks and boosted regression trees. So I'm often working with problems that aren't like points, but it's a spatial map. Say it's sea surface temperature. So imagine you see sea surface temperature for the whole region, and then you're trying to make a prediction for a point. So you are using points. It's just that your predictor is not a point. or you could treat it as a point, but you could also treat it as, hey, I want to be aware of the whole spatial field. And so the models I'm often comparing are convolutional neural networks for two-dimensional data. Predictor variables are two-dimensional, and trying to understand if awareness of the spatial context, so what are the nearest neighbors look like? Are there little swirls? Are there little fronts or whatever like that? Under what circumstances does that help improve the predictions? And yeah, it's been really interesting. Like even in problems where I'm absolutely positive that the spatial context should be helpful, and it does help, but only a little. So I'm still trying to understand that, mostly by like testing different examples and comparing performance. I'm actually going to show an example of that. I think next week I'll compare a boosted regression to a pretty simple, very simple convolutional neural network model. All right. Well, with that, thank you, Haley, for giving us that presentation. And everyone, you'll have the links to things. I'll put the videos up there. I'll get on that. So you can also go to the website for that. And then next week, we're going to be going into, let's see, where are we headed? Starting looking into convolutional neural networks. Right now I have just one session, but I may add a few more onto that. That's obviously a very massive topic. And then after that, we'll be having more sessions on just working with gridded ocean data and, getting you more familiar with different ways you can get data and access that data and work with that. All right, with that, everyone.
Thanks for having me.
Weekend.
Thanks, everyone.
Okay, take care.
Thanks a lot.
Bye.
Take care.